It's happening again. Hello, welcome to our final week of lecture for CSC236. This week we're going to be talking about regular languages and non-regular languages. Before we start, a few reminders. Assignment 3 has been posted and it's due on Thursday. It's very short. Compared to Assignment 2, it's very, very short. If you do want some extra office hours beyond the ones that I normally do on Wednesday from 2 to 4, just let me know. I'm happy to do some, but I haven't seen a ton of questions about it on Piazza yet. There will be one last tutorial this week on Friday, and it will include a quiz, so please do show up. Also, we'll be doing another Q&A session on Wednesday, again from noon to 2. If you haven't come to one of these Q&A sessions, you're missing out on a lot of fun. I really encourage you to show up because it's really great to do problems together and get to have some interactivity. There are some changes to the marking scheme. The vote on Piazza is technically still pending, but after it's been open for a week on Monday, it'll officially be over, and I will post on the course website all of the resulting changes, all of the reweighting. And one of those changes includes a new final assessment to replace our exam. It'll be written from April 7th to 9th, and it'll be worth 20%. And just sort of a meta announcement, please do check the course website or Piazza semi-regularly. Any announcements that are important, I'll post them in both places, or if it's something less important, I'll usually just post it on Piazza. So, regular languages. We're going to define a language as regular if any of the following are true. If there is a regular expression that captures L, or a deterministic finite state automaton that captures the language, or a non-deterministic finite state automaton. And we know, based on the results that we saw last week, that all three of these statements are equivalent. So we know that if there's a regular expression, we can also make a DFSA. If we have a DFSA, we can make an NFSA. We can switch between any of these three representations. So what if we want to prove that a particular language is regular? Well, the most obvious way to do that would be to just directly construct a regular expression that captures the language, or a DFSA or an NFSA. But sometimes we might want to do this more indirectly. So one thing that we can take advantage of is these closure properties of regular languages. So if we know that some other language is definitely regular, and we can make L by taking that other language and doing the complement, or the Kleene star, or intersecting it with another regular language, then that implies that L is also regular. There's also this very useful fact that all finite languages are regular. I don't think this is proven in the Vassos course notes, but it's not very hard to prove. In fact, it's pretty straightforward to come up with a regular expression for an arbitrary finite language. I'll leave that as a thought experiment for you, though. So let's look at an example. So let's define L1 to be strings of zeros and 1 that have length 236. Can we prove that L1 is regular? So this is a case where, sure, we could come up with a regular expression or a DFSA that matches this language, but it would be really tedious, right? We would need a really, really big regular expression. So we're drawn to want to prove this more indirectly. This is a case where we could use the fact that all finite languages are regular. So there are only a finite number of strings of length 236. In fact, something like 2 to the power 236 strings, which is a lot, a whole lot, but it's still finite. So that alone gets us what we want. Let's look at another example. So what about L2? Strings of zeros and ones where the length is a multiple of 236. So this one, we can't use that escape hatch. It's not a finite language. There are infinitely many strings in this language because there are infinitely many multiples of 236. I would suggest pausing this and seeing if you can come up with a proof for this language. So the trick here is that there is a close relationship between L1 and L2. In fact, L2 is just equal to the Kleene star of L1. And since regular languages are closed under the Kleene star, we know this by regular expressions and by the DFSA constructions. This means that L2 is regular. Now, we might ask, are all languages regular? Can we always prove that there's a regular expression or a DFSA? Well, remember that DFSAs, they're kind of like computers that only have a fixed finite amount of memory. And so it would be really surprising if such a limited model of computation could solve, in essence, any problem. And it turns out this is not the case. In fact, we briefly talked about this in week 9 when we first talked about regular expressions, because we looked at this language 0 to the n, 1 to the n, and we puzzled over it and we tried to come up with a regular expression, and many of you were pretty convinced that it wasn't possible to do so. But I said that at that point, we didn't really have the tools necessary to actually prove that there was no possible regular expression for that language. Well, the time has arrived. We now have those tools. We can actually prove that a language is not regular. Before we do that, though, we're going to take a little detour and talk about proving a related property of languages. So suppose we have some DFSA that accepts this language, language of some number of A's where that number is a multiple of 3. So what is the fewest number of states that we can get away with to capture that language? So we might start by just trying to come up with a DFSA that recognizes this language. So let's see, the starting state should be accepting because 0 is a multiple of 3. And then I'm thinking I'm going to have one state that represents like a remainder of 1 mod 3 in terms of number of A's, and then a remainder of 2. And then finally, that'll bring us back to the start state. So we'll call those Q0, Q1, Q2. Well, so this shows that 3 is a sufficient number of states, but there's still this question of, could we have gotten away with fewer? Could we do this with 2 states? Now, I can kind of stare at this and puzzle over it and bang my head against the wall and become really convinced that, like, no, there's just no way that I could solve this with fewer states. But my failure to invent some clever way to do this with 2 states isn't really a proof that it's not possible. But there is a way that we can prove this. And we're going to take a few different strings intuitively that we think ought to be mapped to distinct states. So consider the strings A, AA, and AAA. And let's think about delta star from S of each of these strings. So remember that S is the starting state, of my DFSA, and delta star of some state and some string says, if I start at that state and I process all of the characters in that string, then what state do I end up in at the end? Now, suppose that it's possible to recognize this language with fewer than 3 states. Well, then it would follow that Q1 is equal to Q2, or Q1 is equal to Q3, or Q2 is equal to Q3. They can't all be different states if there are only, say, 2 states or 1 state. But I'm going to show that that leads to a contradiction, that Q1, Q2, and Q3 have to be different. So suppose that Q3 is equal to Q1. Well, that's a problem because I want Q3 to be accepting, right? Because AAA is an element of this language. But Q1 should not be accepting because the string A is not an element of the language. So that's a contradiction. We can't have a we can't have a state that is accepting and non-accepting. And with this second case, it's the same thing. So I want Q3 to be accepting, but Q2 to be non-accepting. Now, what if Q2 and Q1 are the same? So for this one, it's not immediately obvious why this leads to a contradiction, but we have to ask ourselves, okay, what is the value of, suppose we start at Q1 or Q2, they're the same, and we process an A. Do we get to an accepting state? Well, if we do accept that, then that means that we accept the string AA, right? Because when we process A, we go to Q1, and then if we process another A, we go to this next state, but we don't want to accept AA. Well, and if it's non-accepting, there's a new problem, which is that we reject AAA, which is in the language, because AA gets mapped to Q2, and then if we see another A after that, we go to this state, which we're now supposing is non-accepting. So regardless of whether this state that we get to from there after seeing an A is accepting or non-accepting, we reach a contradiction. So every one of these possibilities leads to a contradiction. So that means that we can't have fewer than 3 states. Q1, Q2, and Q3 must be different states. So we sort of implicitly used a principle here called the pigeonhole principle. So here it is in action. We have 10 pigeons and 9 holes. So no matter how these pigeons arrange themselves into these holes, there must be at least one pigeonhole that has more than one pigeon in it. It sounds like a really simple and obvious property, but we can prove some interesting results with it. So in this case, our pigeons were these states, Q1, Q2, and Q3, and our pigeonholes were the total number of states in the DFSA. So if the total number of states is less than 3, then Q1, Q2, and Q3, there must be at least one pair of those that is actually the same state. Or we can think of it in terms of the 3 strings, A, AA, and AAA. So some pair of those must be mapped to the same state. So here's a general recipe for solving this problem of proving some minimum number of states of a DFSA. So depending on how the question is worded, depending on exactly what we're being asked to do, we might need to do part 1. That is, we might need to prove that n is sufficient by actually coming up with a specific DFSA with n states that accepts the language. Because usually we'll want to prove like a tight lower bound. Of course, we could prove that we need at least one state to solve the previous problem, but that's not so interesting. But once we have our n, and we want to prove that n is necessary, what we're going to do is find n distinct prefixes. I'm going to call them x1, x2, up to xn. And then also matching suffixes, which I'm going to call y's. And I'm going to choose them such that the following property holds. So for each y, there is exactly one x, and it'll be the x with the prefix with the matching number, such that concatenating those two strings forms a string in the language. And there's this little detail that I put in a footnote, which is that we can actually get away with having one of the prefixes not having a matching suffix, and we'll see why that is in a second. So once we've found these prefixes and suffixes, we're going to prove a minimum of n states by contradiction. So assume for the sake of contradiction that we have a DFSA that accepts this language with fewer than n states. Now, by the pigeonhole principle, that means that there must be two different prefixes, we'll call them x sub j and x sub k, that go to the same state q. So now we have to think, well, from that state q, what happens when we process the suffix yj? We want it to be accepting because xj, yj is in the language. But we also want it to be rejecting because xk, yj is not in the language. Remember, we said that for every suffix y, there is one and only one corresponding prefix, such that if I append that suffix to the prefix, I get a string in the language. Now, there's this little further detail that I put in the footnote, which is that we can get away with having one prefix that doesn't have a matching suffix. And the reason why is, so in step 3.3 here, I chose y sub j to be the suffix that is going to force a contradiction. I could have also chosen y sub k, right? So it's enough that at least one of my x sub j and my x sub k has a corresponding suffix. So if every single prefix except for one has a corresponding suffix, then for any pair of prefixes, at least one out of the pair will have a corresponding suffix. This is a pretty minor detail, but it will actually come up in this next example. So you might recognize this DFSA from a quiz last week, or no, I think the week before last week. So this DFSA recognizes strings that end in 0, 1, 1. It's a four-state DFSA, and we came up with this, and we believe now that 4 is actually the minimum. So we believe this is an optimal DFSA. So 4 is sufficient. Can we prove that it's necessary? So we need to come up with these prefixes, x1, x2, x3, and x4. We need 4 prefixes and at least 3 corresponding suffixes. So you might want to pause the video and think about what those prefixes and suffixes will be. So the trick that I'm going to use is, because I have this DFSA in front of me, I can actually think in terms of the states. So I'm trying to pick 4 prefixes such that each of these must be mapped to a different state. So I can look at the states and see, well, what strings get mapped to these states. So for example, if I have the string 0, 1, that gets mapped to Q2. And what about the suffix 1? Well, that'll take me to an accepting state, and 0, 1, 1 is a string in the language. Okay, so I've got Q2 checked off. What about Q3? So 0, 1, 1 will take me to Q3. And then I want a suffix that will that I can append to this string to get a string in the language. Well, I guess 0, 1, 1 would work, but it would be even easier to just say the suffix is the empty string. And so far, so good. So if I append the empty string to 0, 1, I don't get a string in the language. And if I append the 1 to 0, 1, 1, I don't get a string in the language. Okay, what about Q1? So the simplest string that'll take me to Q1 is 1. And then how can I, sorry, not 1, 0. And then how can I get from there to an accepting state? Well, if I add a 1, 1, that'll do the job. And also, adding 1, 1 to any of these other prefixes will not give me a string in the language. And now, finally, I need a fourth one, and that's going to correspond to state Q0. And I can just use the empty string for that, or I could have used a 1. And now, what is the corresponding suffix for that one? Well, 0, 1, 1 is a string that I can append to this prefix to get a string in the language. But if I use this, my argument isn't actually going to work. And the reason is that each of these suffixes needs to map uniquely to one prefix. And that's not the case here, because for any of the other prefixes, I can also append 0, 1, 1 as a suffix and get a string in the language. So this will be a case where my fourth prefix doesn't have a corresponding y value. So here we go, and I named the prefixes using subscripts that corresponded to the labeling of these states in the DFSA, just to sort of make it easier to keep track of. So I've got my 4 prefixes and my 3 suffixes. So now how am I going to use these to prove that, that we need exactly 4 states? I'm going to use contradiction. So assume that there's a DFSA with fewer than 4 states. And here's how I'm going to get a contradiction. Well, so first, I want to observe that I have chosen these prefixes and suffixes properly. So by inspection, I can see that each suffix has exactly one prefix such that their concatenation is in the language. Now, suppose that there's a DFSA for this language with fewer than 4 states. That means that there must be some pair of prefixes from x0, x1, x2, and x3 that get mapped to the same state. So let's call that pair xj and xk, and let's call the state that they get mapped to q. Now, I can do this trick of saying, without loss of generality, suppose that j is not equal to 0. I know that either j is not equal to 0 or k is not equal to 0. There's nothing special about j versus k. Well, that means that there is a corresponding y sub j, because there's a corresponding suffix for every x except for x0, such that if I append y sub j to x sub j, then I get a string in the language. So that tells me that delta star, the result, if I start in state q and process the suffix yj, it should be accepting. But then that would mean that we accept this other concatenation, which is not in the language. And that's a contradiction. So this whole supposition that I can do it with less than 4 states is wrong, because it leads to a contradiction. Now we're going to generalize this. We're going to circle back to proving that a language is not regular. And we're going to do it using an infinite number of pigeons. So here's the classic example of a non-regular language. And this is the one that we saw before in week 9. So some number of zeros followed by exactly the same number of ones. Prove that that's not regular. So for sake of contradiction, suppose M is a DFSA for this language. Now I'm going to consider this infinite family of prefixes 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Well, because this is an infinite set of strings, and my DFSA is finite, it says it right there in the name, the F stands for finite, then there must be some pair of strings from this infinite set that get mapped to the same state. So by the pigeonhole principle, there must be some distinct n and m such that n zeros and m zeros both get mapped to the same state. And here's how that leads to a contradiction. So consider delta star q 1 to the n. Is it accepting? If it is, then we are bad because we accept 0 to the m, 1 to the n, where m is not equal to n. But if it's not accepting, we're not doing any better, because we reject 0 to the n, 1 to the n. So both of these possibilities leads to a contradiction. So our assumption that there was a DFSA for this language is wrong. It's not a regular language. This is the point where I would pause and say, does that make sense to everyone? Do you have any questions? And it's so disappointing that I can't do that. But if you do have questions, or if you're confused at this point, please come to the Wednesday Q&A session and bring questions. So here's our generic recipe for doing this. We're going to find an infinite family of prefixes, x1, x2, dot, 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 such that all of those prefixes must be mapped to a different state. We must be able to distinguish between each of them, because for each of them, there is a unique suffix that puts it in the language. And then our proof is going to be by contradiction again. So assume that there exists some DFSA that accepts this. Well, by the pigeonhole principle, at least two different prefixes from our infinite family must be mapped to the same state, which we'll call Q. And again, we're led to this contradiction where we say, well, if we process the corresponding suffix starting from the state Q, we want it to be accepting and not accepting. And so we reach a contradiction. This is very similar to our recipe for proving a minimum number of states for DFSA. We're just kind of pushing that minimum to infinity. So there is another way, and this is actually the way that is done in the Vassos course notes. The David Le course notes do not go over the pumping lemma. They use our sort of pigeonhole principle from scratch approach. And you can use either. So if you find I'm going to do my best to explain the pumping lemma. If you find it inscrutable, don't worry about it, because all that is required of you is you need to be able to prove that languages are not regular. You don't necessarily need to prove it using the pumping lemma or using the other approach. It's up to you which approach you want to use. But you might find this more straightforward, or you might find it interesting. So the formal statement of this lemma is just, it's really hard to wrap your head around. So the pumping lemma says, suppose L is a regular language. Then there exists an N, which we will call like the pumping length. Such that for every string in the language whose length is at least n, the following property holds. And then a bunch of stuff. A whole bunch of stuff. Okay, so we're saying that x can be broken down into the concatenation of three strings, u, v, and w, with the property that v is not empty, and the prefix uv, its length is no greater than n, and for every k, u plus k concatenations of v plus w is also in the language. So here's a more, hopefully more intuitive way of saying this. So if L is regular, then every sufficiently long string in L contains a non-empty part that we can repeat any number of times, and no matter how many times we duplicate that middle part, we can keep on generating more and more strings that are in L. So this is useful because it can also be used to prove non-regularity by sort of using the contrapositive of this property. Well, first, let's talk about just a sketch of how we would prove this lemma. Why is it true? So suppose we have some DFSA M where it has n states. And there's a bunch of stuff going on here in the middle, and we don't really know what it is. And let's consider some string x, which is in the language of M, and such that the length of x is greater than n. Now, here's where we can use the pigeonhole principle. So it turns out the pumping lemma is kind of, again, the pigeonhole principle in disguise. So we have more symbols in x than we have states. And so that tells us that when we process the string x, our path through the DFSA must repeat a state. And it follows from that. So we don't really know exactly what this path through the DFSA looks like. But we do know that at some point along its path, it's going to be returning to some state. And from that, we know that there's a cycle. So here, our cycle is like this. The cycle could also just be literally from one state to itself. But the fact that there was some cycle along the way tells us that whatever the string looks like, we can take the labels along this cycle, let's call them A, B, and C, and whatever prefix of that string, we'll call it U, took us there. If we take U plus ABC plus whatever suffix eventually takes us to the, what was the suffix called? W, I think? Yeah, I'll call it W. So whatever suffix took us to the accepting state. So our string x is going to look something like that. And the idea is, well, because we had this cycle along the way, that means that also something like that is also in the language, because that is also a path through the DFSA that ends in an accepting state. And this is true for any number of repetitions of the string that is formed by the labels of the cycle. So that's a sketch of how we would prove this. It's the pigeonhole principle in disguise. So how can we use this? Well, let's try and show that another language is non-regular, and this time using pumping lemma. So our language is going to be PAL, the language of palindromes. So they are strings that are the same forwards as backwards. Now, suppose, for the sake of contradiction, that PAL is regular. Well, then the pumping lemma tells us that there exists some value n such that every string whose length is at least n has some middle part within the first n characters that we can repeat any number of times. So can you use that to derive a contradiction? I recommend pausing the video and thinking about this for even a few minutes. Okay, so this is all going to come down to crafting a carefully chosen example of some string in the language. So here's my string. So consider the string x, which consists of n zeros with a 1 in the middle, and then another n zeros. So this is in the language, it's a palindrome. And the pumping lemma says that there is some substring within the first n characters that I can repeat any number of times. So then there exists some, let's call it m, in the positive naturals, such that this holds. Actually, sorry, there's no m at this point. It's just an L. So, sorry, this should be n plus m. So maybe it's not immediately clear why this is. So the pumping lemma says that there's, within the first n characters, there's some non-empty part that I can repeat any number of times. Well, any non-empty string within the first n characters of x is just going to be a bunch of zeros. It might be 1 0, 2 zeros, 3 zeros. Let's call it m zeros. Well, it follows that if I add m zeros to this prefix and keep everything else the same, then I should still get a string in L. But this does not agree with the definition. So There's our contradiction. So the pumping lemma, it's tricky to wrap your head around, and it requires some care to use properly. So, for example, keep in mind, you don't get to choose the value of n. N is sort of chosen for you, and you need to sort of react to it. So for some arbitrary n, you need to show that this holds. You also don't get to choose, in this case, the value of m. So you don't know exactly which part of the first n characters of your string is the string that can be pumped. So you need to show that for any middle part of the first n characters of your string, pumping it is not going to give you a string language. But if you can wrap your head around those subtleties, it can lead to very short proofs. So this was a very short proof, sort of quite similar to the one that we would do if we were to apply the pigeonhole principle directly, but maybe a little bit shorter and a little bit more elegant. So that's it for lectures. Thank you, guys. But this is not goodbye, because I will see you on Wednesday for the live Q&A session, and I'll be sticking around on Piazza for all your questions about the assignment and the final. So good luck with all of that, and hope to see you all on Wednesday. Thanks, guys.